Millions of years ago, vast swaths of Earth were covered in dense, humid swamps. As the ferns, trees, and algae died, they sank to the bottom of dark, stagnant waters, slowly building massive layers of waterlogged plant matter. This accumulation is the biological starting point for all fossil fuels. The carbon-rich energy we extract today consists of the physical remains of terrestrial plants, marine animals, and microorganisms trapped under heavy layers of sediment. Because these remains are sealed deep underground, isolated from the atmosphere, they undergo anaerobic breakdown. Without oxygen to facilitate normal decay, the organic matter is instead subjected to the extreme heat and crushing pressure of the Earth's crust. This physical compression requires an immense geological timescale. It takes millions of years of sustained force to slowly squeeze the moisture and volatile compounds out of the buried material. The fossil fuels we mine today are direct records of preserved biological history, heavily compressed into highly dense pockets of energy. Industrial logistics often treat coal as a uniform, identical black rock. Scientific analysis defines coal as a highly heterogeneous, dynamic geological artifact. An individual coal deposit's industrial value and specific energy output are dictated by its thermal history, the precise duration and intensity of its time trapped underground. Furthermore, a coal's physical behavior and the exact types of pollutants it releases during combustion are governed by the specific microscopic organic precursors present in the original prehistoric swamp. To understand modern power generation, we must first dissect the deep geological past of its fuel. This slow, natural process of transforming buried plant matter into a denser, drier, and more carbon-rich material is called coalification. This chart maps the physical progression of the rock. It begins with peat, a partially decayed precursor. With increasing heat and pressure underground, it compresses into lignite, often referred to as brown coal. As geological compression continues, the material hardens further into subbituminous coal, and eventually into bituminous coal. Bituminous coal sits in the middle of the rank classification. Because it provides a balance of high heat content and large natural supply, it is the most common type used for electricity generation today. At the end of the process, the material reaches the rank of anthracite. This is a hard, brittle, dark, lustrous rock containing a high percentage of fixed carbon and very little volatile matter. While the physical hardening is obvious, the critical factors are the invisible chemical transformations happening inside the rock during this pressure cycle. This table outlines the oxygen-to-carbon ratio, or OC ratio, which serves as a key mathematical indicator of coalification maturity. Looking at the data, fresh plant material like cellulose starts with a high oxygen content and an OC ratio close to 1. As the rock matures through lignite and eventually to anthracite, oxygen and moisture are progressively squeezed out. By the time the rock reaches anthracite, the ratio drops below 0.1. As this oxygen is lost and the carbon concentration climbs, the potential heat content, measured in BTUs, increases substantially. When geologists refer to a coal's rank, they are quantifying its total geological cooking time and measuring the resulting energy density. Rank only measures pressure and age. To understand the actual composition, we have to look at coal type. Macroscopic coal is a mixture of distinct organic components. These components are called macerals. Just as regular rocks are composed of different mineral particles, macerals are the microscopic organic equivalent. There are 3 main maceral groups. First is vitrinite, derived from ancient woody tissues like bark and roots. It is the main reactive component when the coal is heated. Second is liptonite, derived from plant secretions, resins, spores, and algae. This group contains high hydrogen levels and forms the most volatile part of the coal. Third is inertinite. It is chemically inert and does not soften when heated. This group derives mainly from oxidized plant material, or charcoal left over from ancient forest fires. These microscopic macerals aggregate into large macroscopic bands visible to the naked eye. These bands are termed lithotypes. This slide details the 4 primary lithotypes found in common humic coals. Vitrane is bright and glassy. Clarane is semi-bright and silky. Durane is dull and hard. and fusane is fibrous and soft, resembling charcoal. This table maps how microscopic macerals distribute themselves within those macroscopic lithotypes. Note the top row. When a band is composed of more than 95% vitrinite, it forms the glassy vitrane lithotype. Conversely, fusane is almost exclusively formed from inertinite, specifically a subtype called fusanite. It is effectively ancient charcoal preserved in the geological record. Coal petrologists carefully map these specific percentage distributions under a microscope to predict how a particular coal seam will react inside a power plant furnace. The physical properties and industrial utility of a chunk of coal are dictated by the specific types of plants that died millions of years ago. Once that coal is pulled from the earth, the narrative shifts from slow geological formation to the rapid mechanical reality of a modern power plant. Converting coal into electricity requires a specific sequence of mechanical processes. It begins when raw coal is fed into a pulverizer, a machine that grinds the rock into a fine powder. That powder is mixed with hot air and blown into a furnace. The combusting coal heats water inside a boiler, creating massive volumes of high-pressure steam. This steam is channeled to spin the heavy metal blades of a turbine engine. This is the crucial step where the thermal energy from the burning rock is physically transformed into mechanical energy. The spinning turbine is connected to a generator. As magnets spin inside copper coils within the generator, that mechanical movement is converted into the electrical current that powers the grid. We must also address the chemical reality of this sequence. Burning these organic macerals rips apart ancient molecular bonds, releasing trapped elements into the environment. This slide details the exact chemical composition being combusted. While coal is mostly carbon and oxygen, traces of nitrogen and sulfur are also present. When oxidized in the furnace, this sulfur creates significant atmospheric pollution, primarily in the form of sulfur dioxide. To mitigate this, facilities use exhaust systems called scrubbers. As outlined here, a mixture of limestone and water is sprayed into the flue gases. The limestone chemically bonds with the sulfur, pulling it out of the exhaust and trapping a wet paste or dry powder. Modern coal plants are essentially massive chemical engineering facilities built specifically to harness the energy and manage the chemistry of ancient prehistoric swamps. We can see how this petrographic model imposes hard constraints on the real world by examining India's domestic energy grid. India's primary coal deposits are known as the Gondwana coal fields. These formed during the Permian period, roughly 250 million years ago. Because they have been subjected to heat and pressure for 250 million years, these fields consist of high-quality bituminous coal. They are energy-dense and account for nearly 98%. This table summarizes the differences. The older Gondwana fields offer high carbon content, concentrated in eastern and central India, while younger tertiary lignite is distributed in the northeast and south. This 200 million year difference determines the fuel quality and geographic distribution that modern infrastructure must navigate. Every time a light switch flips on, that power relies on an uninterrupted chain of events, starting with the specific cellular anatomy of prehistoric forests, driven by the pressure of deep geological time, and finally extracted through industrial engineering.